In the first question, we know that we have similar triangles because we have the congruent right angles, and we also have angle A congruent to itself by the reflexive property. So I'm going to just redraw the two similar triangles, and once again, they're similar by AA. I'm going to redraw the two similar triangles over here. So we have the small triangle, ABC, and we have the large triangle, DEA, the outer triangle. So when we have similar triangles, corresponding sides are proportional. So we want to make sure that the proportion that we pick is correctly set up, meaning it has to be using sides, corresponding sides specifically, from the two similar triangles. And it does need to be set up the same way on both sides. For example, big over small equals big over small, or small over big equals small over big. It has to be consistent. So AC is from small triangle. BC is also from small triangle. So far, so good, as long as these sides are from big triangle and they correspond to the side from small triangle that they're next to. So AC corresponds to AE, not DE. So that answer choice is not good. Moving on to the next one. AB is small, AD is from big, and AB and AD do correspond. BC is from small, and DE does correspond to BC from big triangle. So that is the correct answer choice. The problem with answer choice number 3 is that CE is not one of the sides of either triangle. If you take a look, CE is not part of the small triangle and it's not part of the big triangle. And that's why I highly recommend redrawing the triangle so it's easier to see. And answer choice number 4, DB is not a side of either of the triangles. And if you take a look at the separated redrawn triangles, it'll be more clear to see that DB is not actually a side of either. DB is a piece of the side from big triangle. Moving on to number 2. So we have two similar triangles. We know that the triangles are similar because parallel lines create congruent corresponding angles. And we also have the shared angle C. So small triangle CDE is similar to big triangle CAB. So if it's hard for you to see what matches up and what corresponds, I highly recommend redrawing the two triangles. So we have small triangle CDE and we have big triangle CAB. And remember, corresponding sides of similar triangles are proportional. So CD is 15, AD is 9, but AD is not a side of either triangle. The full side from big triangle is AC, which is 15 plus 9. And that is 24. So for AC, I'm going to stick on 24. We also know that AB is 40. And we are looking for DE. So now I can set up a proportion. It doesn't matter how you set it up. You just need to be consistent and put corresponding parts together. I'm going to do small over big, and the 15 and the 24 correspond, equals to small over big. From here, I'm going to cross multiply and solve. And when you cross multiply and solve for x, you should get a value of 25 for the length of DE. Moving on to number 3. This is another one where we have two similar triangles. Between the small and the big triangle, we have the congruent right angles. And we also have the shared angle A, which is congruent to itself by reflexive. So we once again have AA. This is a situation where I definitely suggest redrawing the triangles with their corresponding parts in order, because as you can see, the two triangles are not facing in the same direction. This one is like upside down, and this one is like right side up. So I'm going to redraw them both. So I'm going to draw the big one, and I'm also going to draw the small one. And I just like to put the right angles here. So in my big triangle, the right angle is at C. And I'll just put B here and A here. You can just imagine that I'm like turning it around, flipping it over the other way. And in the small triangle, the right angle is at D. And since angle A is shared between the two triangles, it has to match up in the two triangles. So if I put angle A over here, it needs to be over here as well in the small triangle because it's got to match up because they correspond because it's shared between them. And that leaves E as the last angle of the small triangle. Now we know that AB is 9 and AB is right over here. That's from the big triangle. We know that BC is 6. That is another side from the big triangle. DE is 4. That is a side from the small triangle. And we're looking for AE, which is another side from the small triangle. So now we can set up and solve a proportion. So let me set up my proportion over here. Once again, it doesn't matter how you set it up as long as you're consistent and you put corresponding parts together. This time I'm going to do big over small equals big over small. In the previous one, I did small over big equals small over big. It doesn't matter. So here I'm going to do big over small, 6 over 4. They just have to correspond, equals to 9 over x. Once again, they just have to correspond. And if I did big over small here, I have to do big over small here. If you cross multiply and solve x, you should get that it has a value of 6 for the length of AE, which is represented as x. Moving on to number 4. This is one that was based on the do nows that we were doing for a whole week, a review of quadrilaterals. We have a rhombus with diagonals that intersect at E. And we know in a rhombus, diagonals are perpendicular to each other, meaning that they form 90-degree angles. We also know that in a rhombus, since it's also a parallelogram, the diagonals bisect each other. So if this whole diagonal AC is 18, each half is 9. And if this whole diagonal BD is 24, each half is 12. You need to find the length of one of the sides. So we can use the Pythagorean theorem because we have right triangles here. We are solving for the hypotenuse. So I'm going to use 12 as one of the legs, 9 as the other leg, and a squared plus b squared equals to c squared. And we're solving for the hypotenuse. So we have 144 plus 81 is equal to c squared. That is 225 is equal to c squared. So c is equal to 15. That works out nicely. Okay, moving on to the next one over here. Right from looking at the diagram, I'm going to think hills or SAS because I'm seeing a big right triangle with an altitude drawn to its hypotenuse. Remember the big right triangle with the altitude creating the two smaller right triangles. If this is 90, this has to be 90 as well. So I'm thinking right triangle altitude theorem. Immediately, my mind is going to, am I going to be using hills or SAS here? So let's read the question and let's figure out which one we are going to be using. So they tell us that AC, which is the hypotenuse of the big right triangle, because remember when we're talking about the big right triangle, this is its right angle. Opposite from the right angle is AC. If you're having trouble seeing what the hypotenuse is, you might want to just redraw the big right triangle without the altitude. So the big right triangle is CAB with the right angle here. So the hypotenuse across from the 90-degree angle is AC. And that's why I'm calling AC the hypotenuse. And I'm going to label that as the hypotenuse. 7 is one of the segments of the hypotenuse. So that's one of the segments. I'll just label it segment 1 and this segment 2. This is the altitude. And these are the legs. These are the legs of the big right triangle. The other two sides that are not the hypotenuse. We need to find the length of BD. So I'm going to put an X here. We are finding the altitude. So I'm going to go to the altitude rule, which is SAS. And if you didn't remember that the altitude rule is SAS, if you're thinking hills or SAS, it's the only one that has A's in it because the A stands for altitude. Now, for SAS, you do need both segments of the hypotenuse. We know that the whole hypotenuse is 16 and one of the segments is 7. So if you do 16 minus 7, we get 9 for the other segment of the hypotenuse. And now we can plug in to SAS. The segments are 7 and 9. And the altitude is what we're solving for here, which is x. If we cross multiply, we have x squared is equal to 63. Using your calculator, you can simplify the radical. And if you simplify the radical, you should get answer choice 1, which is 3 radical 7. But let's say that you didn't remember how to simplify radicals on the calculator and you got to this multiple choice question. And you have radical 63 and you're wondering which one's the same. You always could type radical 63 into your calculator and hit enter and get the decimal version, which is an approximation, but if it's multiple choice, it's just to see which is the same as the answer choices. And you can type each of the answer choices into the calculator and hit enter and see if it's the same decimal as radical 63. So if you do have a multiple choice question, definitely use your answer choices to help you, especially if you arrive at a situation like this where you need to simplify a radical, but you don't really remember how to do that. Okay. Number 6, a lot of people were trying to use Hills or SAS here, but this is not the same situation as before. The other situation was when we had a big right triangle with an altitude drawn to its hypotenuse, creating 2 smaller right triangles. That is not what we have here. What we have here is a small right triangle inside of a bigger right triangle. We do not have an altitude. We do not have 3 triangles. Here we have 3 triangles, small, small, and the large one. So this is not the same situation. The diagram does not look the same. So this is not a Hills or SAS situation. What we do have here are 2 similar triangles because between the small and the big triangle, we have congruent right angles. And we do also have the angle A that's shared between them. So it's congruent by reflexive property. So we do have similar triangles. And if you're having trouble seeing the 2 triangles, oops, that does not look like a triangle. Let me try that again. You can always draw them separately. This is going to be my small one, ADE. And then I'll draw the larger one, and I'll just try to make it look larger over here, BCA. And I'll put the right angles in. I'm a terrible artist. And I'll put the measurements in. So DE was 120. We're looking for BC, so I'm going to label that as X. AE is 230. And AC would be 230 plus 85. So getting confused there. A lot of people were using 85 in their proportions. 85 is not a side of either of the triangles. That's why it's a really good idea to draw the triangle separately. You got to be implementing all of these strategies that we talk about in class. Those strategies are there for a reason to help us avoid making mistakes. So now I can make my proportion. Once again, it doesn't matter how exactly I set it up as long as I'm consistent on both sides and I put the corresponding parts together. I'm just going to do small over big, and those do correspond, equals to small over big. And now from here, you can cross multiply. So that's 230x is equal to, let me cross multiply that way. And then if we divide by 230, that's approximately, because it does say the round to the nearest whole number, approximately 164 yards is the answer here. Next, we have 2 triangles, and we need to say if they're similar. We're told that RS is 6. We're told that ST is 14. We're told that XY is 9. And we're told that YZ is 21. And that angle S is congruent to angle Y. Already, I'm seeing a congruent angle in between the 2 sides. So SAS is coming to my mind. But I do need to see if the sides are in fact proportional. A lot of you guys were finding the scale factor, so I'm going to do the same thing. I'm going to do side from big divided by corresponding side from small. So let me start with xy from the big triangle. Using the letters in the name, xy corresponds to rs, which is 6. And using the letters in the name, yz, which is 21, corresponds to st, which is 14. And if you take your calculator and divide both of these, 9 divided by 6 is 1.5. 21 divided by 14 is also 1.5. So they are proportional. So I'm going to say here, they are similar by SAS to proportional sides with a congruent angle in between. Okay, moving on over here. So now we do have a situation where we have a big right triangle with an altitude drawn to its hypotenuse, creating the two smaller right triangles. So this is a right triangle altitude theorem question. So I am going to be thinking, is this Hills or is this SAS? So they want us to determine and state the length of AB. So we're going to ask ourselves, do we know anything about the altitude? Do we have it? No. Are we finding it? No. So that's going to lead me to believe that I'm going to be using the leg rule. And we do have one of the legs of the big right triangle. So that makes sense. So we're going to be using Hills, which is the leg rule. And if you forgot that was the leg rule, it's the one that has the L's in it. So the hypotenuse is what we're looking for. So I'm going to make that X. That's across from the 90-degree angle. That's AB. The leg is given to us as 6, the one that we have information about. And the segment is the one that's directly below the leg that we're using, which would be 2. So from here, we have 2x is equal to 36. So x is equal to 18. Moving on. This next one over here, I'm going to just zoom out so that way we can see the whole thing at once. Before I even mark my diagram, I know what number 10 is. It's the proof statement. We always end a proof with what we are trying to prove. TA times HA equals to HE times TH. And we have our reason to justify a product. It's the same every time. So many people came in without knowing this reason. No, you cannot write cross multiplication. Even though this reason justifies cross multiplication, the Regents exam does not give credit for cross multiplication as your reason. What you do need to say is in a proportion, the product of the means equals the product of the extremes. And I know why the proportion is true because it's the same reason every time. We're able to prove a proportion because when we have similar triangles, corresponding sides are proportional. Corresponding sides of similar triangles are proportional. So that gives me a clue that I need to prove triangles similar. And 99% of the time, when we have a 2-column proof, that's going to be through AA. So I already got the end of the proof done. I just need to figure out which triangles I'm proving similar. And that's going to come from the proof statement. So from the proof statement, we have TA. Let me outline that. We have HA. Oh, look, already I know one of my focus triangles, triangle HTA. And let's figure out the other triangle that we're proving similar. HE, TH. So let me put in my other triangle here, triangle HEA. Once again, that came from the proof statement. Now we know the triangles that we need to prove similar. So we're looking for AA in those two triangles. And we have a fill in the blank proof here, so it's here to help us out. So our first step has got to be the givens. And notice it's not all of the givens. So some of the givens are going to come later on. I even see a reason down here that says given later on. We are given up here that HM is congruent to AT and that HT is congruent to AM. And now it's asking us why to justify why we have a parallelogram. Well, if you are givens, you can see it's because the opposite sides are congruent. If both pairs of opposite sides are congruent, the quadrilateral is a parallelogram. And now that we know it's a parallelogram, it's asking us to justify why HT is parallel to MA. Well, that's because opposite sides of a parallelogram are parallel. And now it's asking us to justify why angle THA and angle MAH are congruent to each other. Think parallel lines cut by a transversal, because in the previous step, we just proved that we had parallel lines. And notice our letter Z. So what we have here are alternate interior angles, which are congruent when lines are parallel. Alternate interior angles are congruent when parallel lines are cut by a transversal. Be careful. Alternate interior angles are not always congruent. They're only congruent when you have parallel lines. So you do need to make that clear. Now we need to put in the givens that were not included in the givens at the beginning. HE is perpendicular to MEA, and HA is perpendicular to AT. And they even give us the conclusion that we're going to draw from that. That angle HEA is a right angle, and angle HAT is a right angle. And the reason for that is from the given, because we had perpendicular lines, and perpendicular lines form right angles. Okay, now we just need to say why those two right angles are congruent to each other. And that's because all right angles are congruent. So we had our first pair of A's from the alternate interior angles, and our second pair of A's from the congruent right angles. And now we have AA, and after that we have our proportion and our product. And that's that. So even if you were a little bit stuck on this proof, you can use the previous proof to help you out with this one, because ultimately it's the same goal, proving triangles similar and then proving a product. So this one provides you with the structure, especially for the ending, right? That you need to prove a proportion before you can prove a product. So definitely use the other questions. Use the rest of the test to help you. So I'm actually going to start from the ending and work backwards, just like we did in the last one. So I'm going to start my statement reason chart. And I don't know how much space I'm going to need, but I do know I'll probably continue over here just because there's not a lot of space on here when I'm on the computer. So I'm going to start over here and work up. So I'm always going to end my proof with my proof statement. And this is going to be my ultimate goal, to prove the product that AD times CB is equal to DC times AC. And the reason is the same every time. In a proportion, the product of the means equals the product of the extremes. And that reason gives you a clue as to what needs to come first, even if you didn't have the previous question as a guide. But you do need to prove a proportion first, because products come from cross-multiplying a proportion. So before that, we are going to need to prove a proportion, and we're going to take the segments from the proof statement and we're going to arrange them. So I'm going to put AD, I'm going to put AC, I'm going to put DC, I'm going to put CB. I used all the segments. Now let me just double check that they cross multiply to give me the product that I want. AD times CB, that's good to go. DC times AC, that's good to go. A lot of people put proportions that were not cross multiplying to give you the product. Rearrange the segments if it's not cross multiplying the way you want it. And our reason's the same every time. It justifies why we're able to make a proportion. Similar triangles have proportional corresponding sides. And in order to have the proportion, just like the reason states, we need to have similar triangles. So it even tells me in the first part of the proof statement, the triangles that I'm going to be proving similar. And I know in a 2-column proof, it's going to be through AA. So I already did half the proof. I already did the whole part B without even reading the question. Keep that in mind. Okay. Now let's actually talk about what we need in order to prove those two triangles similar. So they already tell us that the two triangles we're proving similar are triangles BCA, which is the whole big one, and triangle CDA, which is this one over here to the left. Important. Okay. I'm going to write down my givens here. So write triangle, ABC. Angle C is a right angle. And CD is perpendicular to AB. That is given. A lot of stuff there. Angle C is a right angle. That's an angle in the big blue triangle. And CD is perpendicular to AB. That means where CD and AB intersect, they form 90-degree angles. They form one here and one here, but this one's not important because we don't need to prove anything about triangle CDB. We only care about the one that's the side of the triangle that we need to prove similar to the big one. That way, we can say that the right angles, the one in the small triangle and the one in the big triangle, are congruent, and we have an A for AA. So I'm going to put that here. So I'm going to put down that angle CDA is a right angle. And that was from the part of the given that perpendicular lines form right angles. And now I do need to say that angle CDA and angle C are congruent to each other. And that is because all right angles are congruent. I need one more A for AA. And since the small triangle is inside the big triangle, it's going to be a shared angle. And the angle that they both share, if you draw them separately, triangle ADC and triangle ABC, you look for which letter is the same in the two triangles. Letter A is the same letter. That's what's shared between them. And if you remember, we did a question exactly like this, literally the same question, when we did the similar triangle proofs for the first time, and also when we did proving products. Both of those days, we literally did this exact question. So also make sure that you study your past stuff from class. Make sure you take notes in class because it is there for a reason. And now we have our proof. That is 7 steps in total. And I will really quickly talk about the extra credit. The extra credit is a coordinate proof. I'm not going to actually do it, but it's a coordinate proof. So no statement reason chart. There's numbers. You're going to use formulas in order to show it. A couple of ways you could have done it. You could, if you plot the two triangles, you'll see that one of them is inside the other, so they do have a shared angle. And then you can use distance formula to show that the corresponding sides from the two triangles are proportional, and you can use SAS. You do need to mention that the shared angle is congruent to itself by reflexive in order to use SAS. Another method is you can take all three pairs of corresponding sides, and using the distance formula, you can show that they are all proportional to each other, that they all have the same scale factor. And that would be SSS, proving that they're similar. Alternatively, what some people did is some people showed that the base of the small triangle is parallel to the base of the big triangle using slope formula. Same slopes means parallel. And then since they knew that the lines were parallel, they knew that the corresponding angles were congruent. And taking that with the shared angle congruent to itself by the reflexive property, they had AA. Any of those approaches would work, but you need to show one of them in a valid way. And you do need to use numbers and calculations because it is a coordinate proof.